Good evening, everyone. Welcome to the doubt clarification and problem solving session for the NPTEL online course on water and wastewater treatment. We are in week 3 now, and this course is being taken by Dr. Bhanu Prakash V from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So, as usual, we will see the contents of this week's lecture. So we started with the water quality parameters, where we discussed about the total suspended solids and pathogens. And then we moved on to the preliminary treatment, where we discussed the basic principles related to the bar screens and the chamber, and we saw the functions of them. And after that, we discussed about the primary treatment, where we learned the basics of sedimentation, the various kinds of settling, starting from the discrete, flocculent, hindered, and compression settling. And then we moved on to the design of sedimentation tank. So I have a few multiple choice questions and also the numerical type questions. So we will solve them one by one. Let's see how it goes. So this is the first question. It says that in the Monod equation, mu represents that substrate concentration at which specific growth rate is half of maximum. So is it true or false? So here we are talking about the Monod equation. So if you try to recall the Monod equation, it is something like mu is equal to mu max into S divided by Ks plus S. So where S represents the substrate concentration and Ks is the half saturation constant. But here we are talking about mu. So mu is not the substrate concentration, it represents the specific growth rate. So accordingly, this is a false statement because mu represents the specific growth rate and the substrate concentration is generally given by S. If we see the diagram of the Monod equation, it is something like this. And when the specific growth rate mu is equal to the half of the maximum, that is mu max by 2, the corresponding substrate concentration is called the half saturation concentration or half saturation constant, which is represented by Ks in this figure. Okay, so according to this question, this is a false statement. Okay, I hope you have understood the problem. Now we will move on to the next question. It says that the municipal corporation must handle a daily volume of 720 meter cube per day of water. It is found that the overflow rate is 16.5 meter per day, the depth is 3.5 meter, and the width is 5 meters. So here we have to calculate the length of the rectangular settling tank designed for the removal of discrete suspended particles would be. So you have been given the discharge and the overflow rate. We also have the depth and the width, but we have to calculate the length of this rectangular settling tank, which will be focusing on the removal of the discrete suspended particles. Please go through the question once more and try to solve it. I'll wait for some time. It's a pretty direct question. So surface overflow rate or overflow rate is the same thing, which is given as 16.5 meter per day. Now we'll see the solution of this problem. So The correct answer is 8.73 meter. We'll see how it comes. So at first, to find out the surface area, the surface area would be the discharge divided by the surface overflow rate. So it would be 720 divided by 16.5. So it will turn out to be 43.64. Now this discharge divided by surface overflow rate will give me the surface area. That is the top part of my reactor. So the top part will be nothing but the length into the width. Okay. So correspondingly, we will equate it to L into B. So my L into B will be 43.64, where the width is already given as 5 meters. So my length will be equal to 8.74 meters. So directly we can solve it. Here, the information regarding the depth is an extra information which will not be required to solve this problem. So you have to be careful, because sometimes we might multiply or divide with the depth term. We have to focus like which corresponding area we have to take for the surface area regarding the calculation. Okay, so we have to be a bit careful around that. So this was regarding the second question, which we solved regarding the length of the rectangular segment. Okay, I hope it's clear. Now we'll move on to the next problem. It says the following data are given for the channel type grid chamber of length 10 meter. The discharge is 0.75 meter cube per second. The depth of the wastewater at peak flow in the channel is 0.8 meter. The width of the channel is 3 meter. So again, length, width, and depth, both all the three are given, and we also have the discharge. Now about the inorganic particle which is being settled. The specific gravity is given as 2.5. The G value is 9.8. Mu is 10 raised to power minus 3 at 20 degrees Celsius. And the density of water is given as 1000 kg per meter. So assuming Stokes' law applies, the maximum diameter particle that can be effectively removed with 100% efficiency is. So we have to apply Stokes' law and find out the diameter of the particle which will be removed 100%. Okay, so maximum size we have to find out for this scenario. Again, it will be in the same way we solved the previous problem, but here then we have to apply the Stokes law. Okay, so we all know that. Okay, first let me give you some time to try this problem, then we will see the answer. So in this question, in these type of questions, it's very important that we maintain the units properly in our calculation, because sometimes the unit may be in meter per second or meter per day or uh, in liters or meter cube. So please make the corrections accordingly, because many times due to errors in the units we may come up with wrong answers. Okay, so here also we have to see that the diameter of the particle is given in mm. Okay, so we have to find the answer in mm. Okay, so we'll see the solution. So the correct answer is 0.175 millimeter. Okay, we'll see how it comes. So at first we'll find the settling velocity. So for settling velocity, we will divide the discharge with the surface area. So again, the surface area, as the previous problem, it will be L into B. So again here, depth is not required. So my Q by L into B, that is 0.75 divided by 10 into 3, will give me 0.025 meter per second. Now, if the particle has to be removed 100%, this will be equal to my surface overflow rate or my settling velocity. Okay, so I will equate it to my surface overflow rate or the settling velocity. So as per Stokes' law, we know that the settling velocity will be equal to rho g into G minus 1 d square by 18. So this is the formula for the Stokes law and Laminar's law. So if we substitute all the values where where d is my only unknown, okay. So we will substitute all the values whatever we have from the question or what we have got from the first step. We will substitute them and we'll find the value of d to be around 0.175 millimeter. So again, just be careful with the units. So this is the answer for this question. Again, it's a very simple and pretty direct question. Just have to make sure then that when the particle is being removed 100%, that means its surface overflow rate will be equating to the settling velocity. That's why we equated Q by dl to the settling velocity. Okay, so just for the third problem, we will now move on to the next problem. It's a theoretical question. Which of the following factors does the sewage load not depend on? You have to say which of the factor is not a factor for the sewage load. So the options are rate of water supply, population growth, infiltration of groundwater, design of sewer system. So think for a minute. Okay, so I think it's a pretty simple question to solve. So the rate of water supply it is directly proportional to my sewage load because however how much ever water supply is being given to a place, the sewage load will be directly be related to it. So to be for calculations, we take around 80 to 85% of the water supply to be taken as my sewage load. And also the population growth and infiltration of groundwater will add up to my sewage load. The more the population, the more the sewage load it will be. But the design of the sewer system, will it be a factor for my sewage load? No, because we have to find out the sewage load and then design the sewer system accordingly. But the sewage load doesn't depend for the design of the sewer system. Okay, the sewage load does not depend on the design of the sewage system. Whatever be the load, we have to design accordingly. Okay, so this is the problem. So here the correct answer is option D, and I have discussed the same thing in the detailed solution. Like sewage load is almost 80 to 85% of the water supply. Okay, and also it will increase if the population will increase. So like that way, the answer for this question is design of sewer system. Okay. So again, just keep in mind that the sewage load doesn't depend on the type of the design of my sewer system, whereas the other three parameters are directly related to the calculation of my sewage load. Okay, the next problem. Select the correct statement regarding screens and the purpose in wastewater treatment. So out of these four statements, some of the statements are true. So you have to find the statements are screens prevent any interference to treatment. Screens are used to protect process equipment. Screens are a part of secondary treatment. There is no head loss when the sewage flows through them. So you can go through the question once again and try to find out the answer. So here we are talking about screens. So as we all know that most of the time screens is the first operation or treatment process which we provide in any wastewater treatment plant. So it is a part of the preliminary treatment. Okay, so it is not a part of the secondary treatment, it is a part of the preliminary treatment. So statement C is incorrect. And also in the statement D, it is saying that there is no head loss when the sewage flows through the screen. But we know there is a head loss when the sewage flows through the screens. And there is a formula also 1 by 2g into capital V square minus small v square, where capital V square will represent the velocity through the screens, and the small v square will be equal to my velocity of approach. Okay. So there is a head loss while the sewage flows through the screens, and also screens are a part of the preliminary treatment, whereas the first two statements are correct. Okay, so the correct option will be A and B. Both of them are the correct statement regarding the screens. And in the detailed solution, I have mentioned what we have discussed, like screens are a part of the preliminary treatment system, and also the head loss through the screens can be calculated by 1 by 2g into capital V square minus small v square. Again, the capital V square represents the velocity through the screens, and the small v square will represent the velocity, the approach velocity in the before this. Okay. So this was the fifth question. Now we'll move on to the next question. It says that select the incorrect statement regarding the grit removal. So now we are talking about grit removal. So the first statement says, in aerated grit chambers, there are no moving parts below the water surface. Second statement, a grit chamber is usually installed after the primary sedimentation tank. The third statement says grit chambers are used to remove oil and grease from the wastewater. The fourth statement says the purpose of a proportional weir at the end of the channel type grit removal, is to measure the rate of flow in channel. Okay, so there are four statements given regarding the grit removal. You have to find out which of these statements are incorrect. So again, there can be more than one statements which are incorrect. Please go through the question once again. Okay, so now we'll see what is the correct answer. So the correct answer is B, that a grit chamber is usually installed after the sedimentation, primary sedimentation time. So this is an incorrect statement because the chamber is usually installed before the primary sedimentation time, not after the primary sedimentation time. Okay, and then the other incorrect statement is it is used to remove oil and grease from the wastewater. It is again an incorrect statement. Okay, so as per the detailed solution, we can say that a grit chamber is usually installed before the primary sedimentation time. Also, grit chambers are used to remove dirt materials such as the sand, ash, clinkers, eggshells, bone chips, and many inert material which are organic in nature and present in the wastewater. Okay, so these are not used to remove the oil and grease from the wastewater. These are used to remove the suspended inorganic particles like the sand, ash, clinkers, etc. Okay, so this is the sixth question which we have discussed regarding the grit removal. Okay, now we'll move on to the next question. It says that for a grit chamber again, given a flow velocity of 0.45 meter per second and a detention period of 45 seconds, the length of the tank should be. So we have been given the flow velocity and then again the detention time. So you have to find out the length of the tank. It's pretty direct question. Just try and find out the answer. I will tell you the correct answer. You hardly require 10 seconds. So we have been given the flow velocity and then the detention period. Okay, we'll see the correct option. The correct answer is 20.25 meter. And how it comes? It comes directly as the length of the tank will be equal to my flow velocity into the detention tank. So time is also given in seconds, the flow velocity in meter per second. So answer will be in meter. So it is 0.45 into 45. So it is at around 20.25 meters. Very direct question for the group chamber. So you can calculate. Okay, we'll move on to the next question. Now it says, for a given discharge, the efficiency of the sedimentation tank can be increased by. So it says that the discharge is constant. Suppose the discharge is constant. Now, if we want to increase the efficiency of my sedimentation tank, how it can be done? Four options are given. Increase the depth of the tank, decrease the depth of the tank, increase the surface area of the tank, decrease the surface area of the tank. So just think about it for a minute and tell the right answer. So it is talking about the sedimentation tank and how the efficiency can be improved when the discharge is being kept constant. Okay. So we'll see the correct answer. The correct answer is increasing the surface area of the tank. Now we'll see how increasing surface area of the tank will help in increasing the efficiency of the discharge. So it says the efficiency of the sedimentation tank generally indicates the overall removal of the suspended particles, okay, at a given flow rate or at a given surface flow rate. Now, the efficiency will increase if the overflow rate reduces. So what does overflow rate reducing means? It means that more time you are giving to the particles to settle down. So obviously, if more time is being given to the particle, okay, so more settling can happen. So to give more time to my particles to settle, my overflow rate should decrease. Now the overflow rate is generally given as we have solved the previous problems as per discharge by the surface area. Okay, so now if the overflow rate has to decrease, the denominator has to increase. That is, the surface area has to increase. Okay, so here the surface area, that is B into L, that is the that has to increase. So as per the options, increasing the surface area of the tank will help me in achieving more efficiency by achieving a reduced overflow rate. Okay, so we have to keep in mind that by reducing the overflow rate, I am doing nothing but giving more time in my system for the particles to settle down. Okay, if this happens, then more efficiency will be obtained for the removal of the organic or the suspended matter. For the removal of the suspended matter. Because here we are talking about sedimentation tank. Okay, I hope you understood the problem. We'll move on to the next question. It says the peak factor is given by peak flow into average flow, peak flow minus average flow, peak flow plus average flow, peak flow divided by average. So very direct problem. We are talking about the peak factor. I think we don't need much time. So it is nothing but the peak flow by average flow. So in any wastewater treatment design system, the peaking factor or the peak factor is the ratio of the maximum flow to the average daily flow in the wastewater system. Okay, so maximum by average is my peak factor. I hope it's understood. Now we will see one more MCQ problem. It says that non-spherical particles will settle dash spherical particles. So we are comparing the non-spherical particles and the spherical particles. So will it settle slower than, faster than, equal as, or same as? So how the non-spherical particle will behave as compared to the spherical particles. Okay, so just think about it for some time. So just think about, like, when a particle is settling, what kind of forces will be acting on a particle and how it would affect it. So generally, during the settling of any kind of particle, it will experience a drag force. And when this happens, because of the non-sphericity of the particle, there will be a shape factor that will be coming into the picture, which will affect the drag force acting on the particle. So in the case of non-spherical particle, the drag force will be more, which will obstruct its settling, and hence it will be slower than the settling of the spherical particles. Okay. So for all flow conditions of wet and laminar, the drag coefficient is also a function of the shape of the particle, and it can be determined experimentally. So generally, for ideal scenarios, we consider the particle to be spherical, but if in case these particles are not spherical, it's a non-spherical particle, then the drag force coefficient will change and it will affect the particle settling, and it will be settling slower than the spherical particles. So this is the 10th question. The next question, it says the degree of treatment required for the wastewater depends on raw water characteristics, desired quality and possible reuse of the treated effluent, state regulated wastewater discharge standards, and all of the above. We have to tell on which parameters the degree of treatment required for the wastewater depends on. So if you see all the options, it's obvious that all of them are correct, because the degree of treatment required will obviously depend on my raw water characteristics, that is my influent water characteristics. And how much treatment I have to give will be depending upon the what kind of quality I require in the effluent. Okay, so the quality will be depending on how I am going to reuse the wastewater, whether I am going to discharge it in the river or in the groundwater, or I am utilizing it again in the case for agricultural case or for flushing case. So in various scenarios, my level of treatment will change. And of course, during the discharge of this wastewater after treatment, it is governed by the State Regulations Act. So with respect to that, again, my degree of treatment will change, because this has to be governed. Otherwise, there will be no standardization in this treatment. So all the three statements are correct for the degree of treatment required for a wastewater. Hence, the correct answer is all of the above. So that's what I have mentioned in the detailed solution also. You can go through it. Okay. So the degree of the treatment required depends on the characteristics of the raw wastewater and the desired quality of the treated water for disposal or use, which is eventually governed by the state regulated wastewater discharge standard or water quality parameters. Okay, so this was the 11th question. Now the 12th question. Sedimentation tanks are an appropriate example of, is it a unit process, unit operation, both A and B, or a biochemical process? So here we are talking about the sedimentation tanks. So what kind of, is it a unit operation or a unit process or biochemical process or both of them? So we have learned about unit operations, unit processes. You can directly answer. So it is nothing but, a unit operation. Okay. Why is it a unit operation? Because this kind of treatment units in which the application of physical force predominant. Okay, so in sedimentation tank, it is governed physically by physical forces. So hence it's a called unit operations. So there are other physical or unit operations like the screening, the grid chamber, sedimentation, etc. What are unit processes? Where some kind of chemical or biological thing is happening. For example, the aeration tank in the activated sludge process. So, but here we are talking about unit operations in which the physical forces predominate. It is simple. Our next problem. It says identify the correct statement concerning advanced wastewater treatment process. Okay, so the statements are disinfection is typically considered an advanced wastewater treatment process. Selective ion exchange is used for removal of nitrate from secondary treated effluent. C is both A and B. The D statement says carbon adsorption is primarily used for suspended solids removal from secondary treated effluent. So we have to tell about which of the option is correct. So it's pretty easy. Both A and B are my correct options because disinfection is an advanced treatment. And also, the selective ion exchange can be used to remove the nitrate from my secondary effluent treatment. Okay, so both A and B are correct. Whereas carbon adsorption is not primarily used to remove the suspended solids from the secondary treated effluent. So both my option A and B are correct. So option C is the correct answer for this problem. All these questions are very theoretical. So we will have some more numerical problems in the coming slides. Just wait for some time. Okay, so the next question now. Intermittent sedimentation tanks. So four statements are given. Store water for a certain period and keep it in complete rest. Allow water to flow at a reduced velocity for a significant time. Are also known as continuous flow type tank or none. So here we are talking about intermittent sedimentation tank. So as the name suggests, it is intermittently up there in the treatment plants. So intermittent sedimentation tank, so it's nothing but it is used to store water for a certain period and it is kept in complete rest. So there is no flow, so there will be no velocity. So option B is incorrect, and also it is not a continuous flow type tank. Okay, so it stays in complete rest, or it can be also called as quiescent type tanks. Okay, so intermittent tanks or quiescent type tanks. I hope it's understandable to all of you. We'll now move on to the next problem. It says, which of the following is not an assumption of the Stokes law? So we have seen, I think, the second problem regarding the application of Stokes law to find out the diameter of the spherical particle, which can be removed 100%. So it is saying which of the following is not an assumption of Stokes law. So we will go through the statements. Particle settling is independent of the influence of other particles. The medium is of infinite extent. Reynolds number is less than 100. The flow is laminar. So which of the following statement is not an assumption of the Stokes law? So we'll discuss. So in Stokes law, we assume that there is discrete settling. Okay, so the particle settling is independent of the influence of other particles. So option A is correct. The medium is infinite. Okay, we consider that the medium is infinite, so there is no influence of other factors also. And also the flow is laminar. Okay, but about the Reynolds number, it should be less than 1. It should not be less than 10, it should be less than 1. So hence option C is incorrect, and it is not an assumption of Stokes law. Okay. I think the slides are okay, it's changing. So option C is the correct answer. That is Reynolds number less than 10. It is not an assumption of Stokes law. Assumption of Stokes law says that the Reynolds number should be less than 1. Okay. So the next problem, it says that the surface overflow rate of a settling tank is V. The settling velocity is U. So what will be the ratio of removal efficiency of particles having a velocity less than the critical settling velocity? So now my settling velocity is U, the surface overflow rate is V. So both are different. So I have to find out the removal efficiency of particles which are having velocity less than the critical settling velocity, which is less than U. Okay. So we have four options: 1 minus V by U, 1 minus U by V, U by V, and V by U. We have four options. So if you remember, if we have to find the size of the particle which will be removed 100%. So at that time we will equate V into U. We will consider that the surface overflow rate is equal to my settling velocity. But in this case, it is saying we have to find the efficiency of those particles which have a velocity less than the critical settling velocity. Okay, so obviously the removal will be less than 100%. So how much it will be? It will be equal to my U by V. Okay, so for a given flow rate, if the particles if the particles are having U greater than or equal to V, then it will be removed completely. But for the remaining particles, it will be removed with the ratio of U by V. Okay. So I hope you have understood this problem. Our next question. The type of settling most likely to occur in a real sedimentation tank is. So what kind of settling would we expect in a real sedimentation tank? So though for our design or any particular case, we go for discrete settling. As we discussed about the Stokes law, we go for discrete settling. But here we are talking about the real sedimentation tank. So generally, in real sedimentation tank, the particles tends to agglomerate with each other. They will form flocks. So hence, it will be a flocculant type of settling. Okay, all the particles will come together and exhibit a natural tendency to agglomerate. So hence it will be a flocculent type of settling. It will not be discrete or anything. It will be a flocculent type of settling, or I can say type 2 settling. The other options here are given of type 1 and type 2. So it's a type 2 settling, flocculent settling. Okay, so now we'll move on to the next problem. So it's kind of small numerical, you can say, or it's a one-liner answer, sorry. So the question is, the surface loading rate of a 0.02 millimeter particle is 0.02 centimeter per second. So the particle size is 0.02 mm and the surface loading rate is 0.02 centimeter per second. Now compute the efficiency of removal of a particle of size 0.024. Okay. So the surface loading rate of a 0.02 mm particle is 0.02 centimeter per second. What will be my efficiency of a 0.024 millimeter particle? So I think we don't have to calculate here anything. Okay, all the options can be misleading, so there is no calculation required since my given particle size is more than the surface loading rate. So obviously it will be removed 100%. Okay, so the answer is 100% because all the particles having size more than the size of the particle for which the surface overflow rate is calculated are removed 100%. So 0.024 is more than 0.02, hence it will be removed 100%. Okay, so there is no calculation required in this question. Okay, we'll move on to the next problem. Match the target pollutant with the wastewater treatment unit list. So we have large floating matter, suspended inorganic matter, suspended organic matter, dissolved organic matter, and on the other side we have tripping filter, primary clarifier, wet chamber, and stains. So try to match the correct option with one another. I hope you might have found the correct match. So option is C. We'll see how it comes. So for large floating matter, so large floating matter are generally removed by the primary treatment. So that is a screen. So large floating matter which can affect my other pumps or other things. So it has to be removed at upfront. So screens is the right answer. With the suspended inorganic matter, as we discussed, all type of suspended inorganic matter or the GERD type of matters are removed by my grit chamber. So option 3 is the correct match for B. Right. I think there's some issue. Just hang in for some time. Okay, so we are back online. So yeah, so where were we? We were discussing about the suspended inorganic matter. So it will be definitely removed with the help of the heat chamber. Now the suspended organic matter. So suspended organic matter are generally removed by the primary clarifier. While they will agglomerate, we will see we saw the flocculant type of settling, and then it will be removed. And then at last the dissolved organic matter, which are easily accessible to the microorganisms for their degradation. So it will be done in the trickling filter. So with option D, the first trickling filter is a match. So hence option C is the correct option for this. Okay. So that's what we have discussed. It's given in the detailed solution. We'll see the next question now. Which of the following is not an objective for providing an equalization tank during the sewage treatment? So we are talking about the equalization tank objectives. So which of the following is not an objective for the equalization tank? So we have the options as balance the fluctuation in the flow of sewage, balance the fluctuation in concentration of sewage, assist in self-neutralization, and removal of organic matter. Okay, so we are talking about the equalization tank. So obviously option B is the correct answer for this because equalization tank doesn't deal with the removal of the organic material. Okay, so the primary objective is to balance the fluctuation in flow or concentration or to assist in self-neutralization. So all the three options are correct and option D is not an objective. So as per our question, option D is the right answer. Okay, so that is the main function of the equalization tank for assisting in self-neutralization when balancing the fluctuation of the flow or the concentration of the sewage. Okay, so now some small numerical problems before going into the larger type. So it says that a BART screen is installed in a wastewater treatment plant receiving a daily peak flow of sewage of 50 ml. So the daily peak flow is 50 ml. Now estimate the head loss emitted through the screen considering the desired velocity of flow through the screen as 0.8 meter per second and approach channel area of 0.86 meter cube. So in the starting of our class, we have discussed about the screens and we also found out that while passing through the screen, there will be a head loss. And we saw the equation of the head loss, that is 1 by 2g into capital V square minus small v square, where capital V square is the velocity through screens and small v square is the approach velocity. So in this question, they are asking us to calculate the head loss again. So please go through the question once again and then we will discuss. Okay, so I think you might have found the answer. So the correct answer is 0.014. We'll see how it comes. So basically, you have to find out all the parameters of that equation. So the maximum flow is given as 50 mld, or we can say 50,000 meter cube per day, and we change the unit to meter cube per second because that will be uniform throughout the equation. So we have found out Q in terms of meter cube per second. Then the velocity that is through the screen, that is capital V, is given as 0.8. So one of the V we have got, capital V. Now we have to calculate the small v. So how we will calculate? Now the approach channel area A is given as 0.86 meters square. Okay, so the approach channel area is being given, And what will be my net area of the screen? My net area of the screen will be the flow rate divided by the velocity. So flow rate by velocity will be my net area of the screen. That is how much wastewater is passing through the screen. So that area, the net area of the screen, we have found out 0.72 meters square, since the velocity, the discharge is equal to velocity into area. So now we will just do mass balance to find out the velocity of the approach channel. So we can see that the small v will be equal to capital V into capital A divided by small a, that is 0.8 into 0.72, right? 0.86 is equal to 0.67. Okay, so like this we can find out the small v and then directly substitute into our equation, that is 1 by 2g, which is nothing but equal to 0.0729 into capital V square minus small v square. So if you input all the values, we will get as 0.014 meter. Okay, so this is very simple, right? So basically we have to find out what is my capital V square and small v square. So capital V is directly given in the question as 0.8. So for small v, we have to find out the small a and the capital A. So small a, that is the approach channel area, is given in the question, and the net area can be found out by discharge by velocity. Okay, so in that way we can find out the small v also. Okay, we'll move to the next question now. A grid chamber of dimension 12 into 1.5 into 0.8 meter of liquid depth has a flow of 720 meter cube per hour. We have to find out the surface loading rate and detention time. So four options are given. So the dimensions of the grid chamber is being given with the flow rate. So we have to find the surface loading rate. So again, for surface loading rate, we will discuss it now. So again, for the surface loading rate, we will just divide the flow rate with the top area. So as we have done numerous times, so Q divided by top area. So top area will be length into breadth. So it's nothing but 720 meter cube per hour divided by 12 into 1.5. So we will get as 40 meter cube per hour per meter square. But since some of the options are given in liters, so we will change to 40 into 40,000 liter per hour per meter square. So correct option will be option B, and also option D rather, because you have to find the detention time also. So detention time is nothing but the volume divided by flow rate. So volume is nothing but 12 into 1.5 into 0.8 given in the question divided by the flow. So it will be 0.02 hours because my flow rate is given as meter cube per hour. So if we change the 0.02 hours into minutes, we will get 1.2 minutes. Okay, so option D is the correct answer. So just by solving half of the problem, you cannot select the correct answer because it also depends upon my detention time. So we have to be careful and we should not go for the correct option just by solving half of the problem. So it can mislead us. So it's better to solve the whole problem and then look for the correct option. Okay. So now the next question. It says calculate the settling velocity of a particle having a radius of 0.0075 millimeter and a specific gravity of 2.6. Now assume the viscosity as 10 to the power minus 3 kg per meter per second. So again, it's again a direct question for settling velocity. We have solved it before. So I will just quickly go through it. So it's nothing but 0.0002 meter per second. So first we can find out the kinematic viscosity, that is nothing but my viscosity divided by the density of water. So 10 to the power minus 3 divided by 10 to the power 3. So 10 to the power minus 6 is my kinematic viscosity. And then we will just input in the settling velocity formula, g by 18 into ss minus 1 into t square by mu. So we will just input all the values there and we will get the answer as 0.0002 meter per second. So again, we have to be careful because diameter is not given, so radius has to be multiplied into 2, and again it is given in mm, so we have to convert into meters. The rest all the are in the same units, so nothing to worry about. We will get the answer as 0.0002 meter per second. Okay, so now the next problem. The particle concentration is high and they remain at a fixed position while settling. So such type of settling is called. So here we are talking about high particle concentration, and also they are remaining in fixed position while settling. Like with respect to each other, the relative positions are same. What kind of settling is this? Is it type 1, type 2, type 3, type 4? So it's a pretty direct question. It's a type 3 type of settling because it is a kind of hindered or zone settling where the interparticle forces are sufficient to hinder the settling of the particles, and the particles tend to remain in fixed position with respect to each other. So this happens typically in the activated stage process, in the settler of the activated stage process in the secondary clarifier. So it's a type 3 type of settling. So my last MCQ problem for today is this. It says that the average flow in a municipal wastewater treatment is 4,000 meter cube per day. Determine the approximate diameter of a circular primary clarifier to remove the suspended solids at average flow. Assume the overflow rate as 20 meter per day and depth as 3 meters. So we have been given the discharge, and we have to find out the diameter of the clarifier, which is a circular type of clarifier, so just the diameter. And it's for an average flow that is given as 4,000 meter cube per day, and the overflow rate is 20 meter cube per day and with a depth of 3 meters. So try to solve this problem. Okay, so we'll see how to solve this problem. The correct answer is 16 meters. So Q and Q naught, that is my surface overflow rate, is given as 20 meter per day. So my area, my surface area will be equal to Q by Q naught. Okay, so 4,000 by 20 is 200 meters square. So once we get the surface area, we just have to find out the surface area of a circular primary clarifier, and we will equate it to find the diameter of the clarifier. So it's nothing but d into square root of 100 into 4 by pi. It will come out to be 60 meters. Okay, so it's a pretty direct question. So I think we have solved all the numerical multiple choice type of questions, small questions. So now I'll take up a few numerical type of subjective type of question so that it will help you in understanding the concepts better. So we'll start with a design problem. We'll see how to go on about it. So let's see. It's subjective type problem. So we have to design a screen chamber. So it says design a bar rack and a screen chamber for a peak design flow of 150 mld. So it is talking to design for a peak flow where the average flow is 50 mld. So 3 is the peak factor. So the following data are given that the peak design flow is 1.736 meter cube per second, and this is the condition of the incoming trunk sewer, because before the stream shower there will be some sewer line that will be coming. So the incoming sewer tank has a diameter of 1.4 meter, The depth of the flow at sewer in sewer at peak flow is 1.5 meter. The velocity is 1.16 meter per second. The drop in the screen chamber flow to invert is 0.08 meter. Assumed width of the rectangular bars in my screen is 10 mm and the clear spacing between them is 25 mm. Okay, so this is a design problem. So the basic primary design parameters are given to you. So based on that, you have to design the screen chamber. Okay, so I will show you diagrammatically like what are all these things. So it will help you understand better. Yes, we can take a screenshot or go through. We'll discuss like how to solve this problem. Okay, so we'll see how to solve this problem. So this is week 3. So what were all the given data? So we have the Q peak as 150 mld, or we can say it as 1.736 meter cube per second. Okay. Now the dia of my sewer is 1.4 meter and the depth of flow is given as 1.05 meter and the velocity of flow is 1.16 meter per second. Now the drop of my screen chamber flow to invert. I will show you diagrammatically what does it mean. Is 0.08 meters. Now, and for my screen chamber, the bar width is uh, given as 10 millimeter and center to center spacing, or rather clear spacing is given. So clear spacing is given as 25 mm. Okay, so I'll just make a diagram, small diagram. Suppose this is the pipe. There is a sewer pipe that is coming into the system. So there will be a drop, and then this is my screen chamber. And suppose these are my screens. So I'm viewing it horizontally. So this is my inclined screen. So suppose this is my level of water. Okay. So after the screen, there will be a small head loss. So it will decrease a bit. Okay. Now this diameter of pipe. This diameter of pipe is this is given as 1.4 meter. Okay, the diameter of pipe is given as 1.4 meter, and this invert level is given as 0.08 meter. Though it looks a big one, but I've drawn just to show you it is very small as compared to the diameter of the pipe. Okay, and I will suppose I'm taking this as my datum, this as my datum, and I will take this distance just for starting as Z1, and this distance I am taking as Z2. Okay, so now, so this is the whole diagram of my screen chamber. I will see how to solve this problem. Okay, so we'll first start with my design of bar rack. So at first we have to assume velocity of flow through rack openings. So this data is not given. So for multiple choice question, this data will be given, but for design problem, it is not given. We will assume it to be 0.9 meter per second. Okay, 0.9 meter. So what will be my clear area? My clear area of openings. Since this is the velocity through my screens, so my clear area through racks, it will be equal to Q by my V. Okay, so Q I know is 1.736. V I have assumed at zero point 0.9, so it will be 1.929. So suppose this is my cross-sectional area of my screen's chamber, and I will suppose this is my cross-sectional area. These are my screens. Okay, these are my screens, or I will show these are my racks. Okay, these are my racks. So what I can say that we have to find out this area which I am highlighting in yellow. This is my clear area through which my wastewater is flowing. Okay, this all this area, and this area is my clear area. So what will be my this area? Total area will be divided by Q by V. So this is equal to 0.929 meters square. Okay, I hope you have understood. So since this is the clear area and we know the depth of flow, we know the depth of flow. So we can find out the clear width, clear width of opening through racks. Okay, so it will be equal to 1.929. That is equal to my area divided by the depth. Okay, area divided by the clear depth. So it is 9.129 divided by 1.05. It is given in the question. So it is equal to 0.84. So now this this area, this width plus this width plus this width, or the three width, everything together will be equal to 1.84 meter. We don't know the number of bars. We have to find out the number of bars and number of clear spacing. But the total width of clear width is 1.84 total, not one. All the total three together will be equal to, or how much ever openings are there, it will be equal to 1.84. So we have just, this is my depth of flow. Okay, here it is shown. So it will be 1.84. So my number of clear spacings required. So my number of clear spacing will be equal to 1.84 divided by my one's clear spacing between bar. It is given as 25 mm, so 0.025. So it will be 73.6. So hence we can provide. So this is my final thing for the bar racks that provide 73 clear spacings of 25 mm each. Okay, so my number of bars will be one less than the clear spacing, 73 minus 1, that is 72. Okay, so so provide 72 bars. What is the size? Size is 10 mm each. Okay, so my, so again the total width of my screen chamber. How much it will be? It will be 73 into 25 mm, so 0.025 plus 72 into 10 mm, so 0.010. So it will be equal to 2.545. So this is my total width of the screen chamber. Okay, so pretty simple. I will just quickly go through it. So first we will find out, we will assume the velocity of flow through the rack opening, okay, at point 0.9. Then first we will find the clear area of the openings. So the clear area is Q by V, velocity. Then the clear width, that is my area by depth. So I found out the clear width. Now number of clear spacing, that is my clear width divided by the width of each spacing. So we have provided 73 clear spacing of 25 mm each. So my number of bars will be equal to 73 minus 1, that is 72. So provide 10 bars, 10 bars of 72 numbers. Okay, so my total width will be 73 into 25 mm plus 72 into 10 mm. So this is my screen chamber. Now, initially I have taken some Z1 and Z2 parameters. So now we will try to find out these two parameters. Okay, we have to find out these two distance also, because ultimately we have to find out the head loss through my bar rack. Okay, so just before that, suppose this is my section 1, okay, and this is my section 2. So I'm taking two sections, section 1 and section 2. Section 1 at the sewer pipe and section 2 before the sewer line, before my screen chamber. So we will just simply applying Bernoulli's theorem, that is the total energy is conserved. So applying Bernoulli's theorem at section 1 and 2. So what will we get? It will be Z1 plus D1 plus V1 square by 2G is equal to Z2 plus D2 plus V2 square by 2G plus HL. HL is the head loss from sewer line to my approach channel. Okay, so here my HL, the head loss will be equal to some K factor into V1 square by 2G minus V2 square by 2G. So this is the head loss due to the sudden expansion from sewer to the screen chamber. So this is not the head loss through the screens, this is from sewer to the screen chamber. So now we will be taking the floor level as datum. Okay, so once we take the floor level as datum, my Z2 values will become 0. So my Z1 value is 0.08, that is my invert level, plus the D1 is my depth of, what was D1? D1 is one depth of flow. Okay, so it is 1.05 plus V1 square by 2G V1. So my V1 is 1.16 square by 2 into 9.81. Now I have taken the flow level as datum, so my Z2 will be equal to 0. Now D2 I don't know. Okay, so D2 is the parameter which I have to find out. Okay, D2 is the parameter that I have to find out. That is nothing but this thing. This is my D2. This was my D1, 1.05 meter. So D2 I have to find out, plus my V2 square. So plus my V2 will be Q by area, 2.545 into D2, the square by 2 into 9.81, and then my HL. HL will be the K value which I am taking is at zero point 0.3. So 2 into 9.81, 1.16 minus 1.736, 2.545 D2 ka whole square. Okay. Will you simply will solve this? So we'll get one cubic equation. So D2 cube minus 1.178 D2 square plus 0.0166 is equal to 0. So if you solve this cubic equation, you will get D2 as 1.71 meter. Okay, so if you get D2, my V2 will be equal to the Q into area. Area is width is 0.545 into 1.71. So it will be 0.583 meter per second. So we have D1, D2, we have V1 and V2. We have got all this, all the four things. Okay, so at last we will now find out. So now to find out the head loss, we need the velocity, my velocity through the screens. Okay, so my velocity through the screens. So my velocity through clear openings. So clear openings of bar rack. Okay, so my capital V will be equal to the flow 1.736 divided by the area. So what will my area? My area will be 73 into 0.025. This is my breadth into height. I have found out 1.17. So it will be equal to 0.813 meter per second. Okay, so in the first case, I assumed it to be equal to 0.9. So it is approximately 0.9 meter per second. So it is almost correct. Okay. So what will be my head loss? My head loss will be 1 by 2g v square minus small v square. So 1 by 2 is 0.079 into v square is 0.813 square minus v2 square is 0.583 square. So I will get it as 0.0234 meter. So this is my head loss. Okay, so in this way I can clearly solve this problem. Got it? So we just have to, so after finding the width of all this, we will take two sections, that section 1 and section 2. Section 1 will be in my sewer pipe and section 2 at the start of my approach channel. So we will apply the Bernoulli's theorem. So if you see the Bernoulli's theorem, Z1 plus D1 plus V1 square by 2G is equal to Z2 plus G2 plus V2 square by 2G plus the head loss. So head loss is due to the sudden expansion. So it will be k times the coefficient into the difference in the velocity head in the two sections. So we'll just fit the values and we'll find out the depth of flow in the approach channel. So my depth of flow in the approach channel is D2, that is 1.17 meter. So once we get the depth of flow in the approach channel, we will find the velocity of flow in the approach channel. Or we can say this is my small v for my head loss. Okay, so like that, we will get the velocity of flow in my approach channel. Now we will find the velocity through the clear opening, which is my capital V, which is my capital V. Okay, so it's just very simple. Then we will just substitute the values for the head loss in the equation. So in that way, we will design the screen chamber. I hope it's understandable to you. If you have any concern, you can get back to me in my email address. Okay, this is a very standard problem for the design of the screen chamber. I hope you might have solved many of your queries because this one problem will take care of many concepts. Okay, now we'll see the next problem. So the next problem says a water with a design flow rate of 300 liter per second is passing through a rectangular channel, has a maximum flow velocity of 36 meter per minute. A screen is to be installed in the channel using 10 mm thick bars with 30 mm clear openings at an inclination of 50 degree to the direction of flow. Determine the velocity through bars and head loss in meters. Assume width to depth ratio of the channel as 1 is to 1.5 and coefficient of discharge as 0.7. So again it is related to the screen chamber. Okay, but here there is an inclination to my system. Okay, so again a pretty simple question. Let's go through a question answer and then we will discuss. Okay, we'll see how to solve this problem. So this is my question number 2. So it says that my Q is 300 liter per second. It's a rectangular channel. It's a rectangular channel. Okay, so my maximum flow velocity is 36 meter per minute. Okay, the bars are 10 mm thick and the clear space is 30 meter and the bars are inclined at 50 degrees at 50 degrees. Okay, and the width to depth ratio is given as 1 is to 1.5 and the coefficient of discharge CD is given as 0.7. So we'll solve this problem again. So first we will find out the clear area AC. So my clear area will be the discharge by the velocity of approach or my maximum flow velocity. So my discharge is 300 liter per second, or we can write 0.3 meter cube per second, and my velocity is given as 36 meter per minute. So I will write 36 by 60 meter per second to make the units same. So it is 0.5 meter square. Now also my this area can be find out into width into depth. Okay, so width is W, my depth is 1.5 of W because it is the ratio is being given 1.15 rather, or is it okay? Sorry, it is 1.5. Okay, 1.5. So it will be equal to 1.5 W square. So we know AC as 0.5 is equal to 1.5 W square. So my W will turn out to be 0.7577 meter and my D will be 1.5 into 0.577 meter, that is equal to 0.833 meter. Now this would have been the area, this would have been all the case if it is all straight. Now my screen is inclined, so my effective area will now become as A clear divided by sine 50 because it is inclined at 50 degrees. So it will be sine 50. So 0.5 divided by sine 50 degree, that will be 0.653 meter square. So now my net area will be equal to my effective area into spacing divided by the spacing plus dia. Okay, so my effective area is 0.653 into 30 divided by 30 plus 10. So it will be, my net area will be 0.49 meters square. So again, with the help of continuity equation, my velocity of flow will be equal to how much? 0.6 into 0.5, all are given by 0.49. Because I can write velocity of approach into clear area is equal to Vf into net area. So by continuing equation, I can find out the velocity of flow. So it will be 0.612 meter per second, and it is also less than 0.9 meter per second. So this is okay. Okay. So at last, I will just calculate the head loss. HL is equal to 1 by C, since we have the coefficient of discharge, so we have to take it into account. So 1 by C into 1 by 2G V square minus V square. So 1.0.7 into 1.1 by 2 into 9.81 into 0.612 square minus 0.6 square. It will be 0.001180. So pretty simple. Again, we have to find the velocity of flow, the velocity of approach, and then we will just find out the head loss with the help of these data. So it was pretty simple, and right, just here one change you have to do, that I have to take the effective area including my inclination. Okay, if I don't take this, then my problem will be incorrect. So this is a small change, otherwise everything is same as for the last problem. Okay, I hope it is understandable to all. Okay, so we will solve one more problem. So these were the answers of this question. So one more problem. So it says that a grit removal facility is designed to treat a flow of 18,800 meter cube per day. The length, width, and depth are given as 18, 0.73, 1 respectively. Calculate the overflow rate, the terminal velocity Vt, are the smallest particles that will be fully removed, then the horizontal velocity and the detention time. So just four small parameters we have to find out. It's pretty simple. It is, we have solved all these problems separately, just that I have clubbed all these things for a complete problem. Okay, so a grit removal facility, the discharge is given, the length, width, and depth is also given. We have to calculate these four parameters. We'll see how to go about with this. So this is my third problem. So here Q is given as 18,800 meter cube per day. L is 18 meters. W width is 0.73 meters, and my depth is equal to 1 meter. Okay, so first we will find out the surface overflow rate. So for surface overflow, so we'll find out the surface overflow rate. So for surface overflow rate, the surface area has to be found out. So my surface area is nothing into length into width, that is 18 into 0.73 is equal to 13.4 meters square. So my surface overflow rate SOR will be equal to Q by SA, surface area. So it will be 18,800 meter cube per day divided by 13.4 meters square. So it will be 4131 meter cube per meter square per day. Okay, simple one liner, just the SOR will be equal to 411431. Now the velocity, terminal velocity of the particle. So again, we will just, it will be same as my SOR. So I will just change the units into of this. So it is given as 1431 meter cube per meter square day. I will just change the day into minute. Okay. So per day will be equal to 24 into 60 minutes. So it will be equal to 1 meter per minute, or I can write it as 0.017 meter per second. So my surface flow overflow rate is will be equal to my settling velocity. So I just change the units of this to find out the answer. Now option C was my horizontal velocity. My horizontal velocity VH. Now my horizontal velocity will be equal to again the discharge, but this time I will take not the top surface area but the side surface area, that is D into W. So it will be 18,800 meter cube per day. I will change it to seconds. So meter cube per day into 24 into 60 into 60 seconds. I just change it into seconds divided by 1 meter depth into 0.73 meter depth. So it will be coming as 0.30 meter per second. So my velocity of flow is 0.3 meter per second. And at last, we have to find out the detention time. So detention time. So for that, we have to find the volume first. So volume is L into D into W. So it will be 18 into 0.73 into 1, which is equal to 13.4 meter cube. And so my detention time theta will be equal to V by Q. So V is 13.4 meter cube and Q is 18.800 meter cube per day. And if I change it into second, day by 24 into 60 into 60. So my detention time theta will be equal to around 60 seconds, or I can say it is 1 minute. So generally grid chambers will have very small detention time around 1 minute or 30 seconds. Okay, so these were all the questions. So simply it's a very simple problem. It's just that I clubbed all these small parameters and made it a large problem. Okay, so I hope you have understood all this. So the correct answers are given here. You have solved the problem. So thank you everyone. This was all the content which I had for this week. So our next session will be again on 16th of February at the same time, 7 to 9 p.m. on Friday. And if you have any queries regarding this week's lecture or anything from week 1, week 2, or week 3, or you want any other help in the form of extra questions and all, you can get back to me in my email address, that is saha19akash@gmail.com. Okay, so thank you everyone.